In this video, we're going to examine the indicator variables and how we inject that into R to create regressions that can do either replicate the t-test with a simple binary indicator variable, but we'll also look at an example with multi-category factors and how we include those into R for our system. So the first thing I'm going to do here is I'm going to run a couple libraries. I'll library the tidyverse and the log5 data so we have some data sets. And the one I'm going to look at first is this commute Atlanta data set. And I just looked at the head here. We're looking at commute times based on the distance that they've traveled, the time it takes for their commute, their gender, their sex, and their age. Pretty simplistic data set. I mean, we're going to look at something that's fairly obvious, but we're also going to examine a few other not as obvious things here. The first thing I want to examine is I want to ask myself the question, I wonder if males and females, if the time that they take to drive for their commute, the time that they've chosen to take for their commute is different. Is there a difference between males and females? And if we think hard about that, I think we would agree that that's just a t-test. So I want to know if the time is broken down by sex is any different. And I have to tell it again, my data set is the commute Atlanta. And I'm just going to leave it like that because I'm really saying, is there a difference between the average time of commute for males and females? When I run that, I come down here to the bottom and I see that the time by sex, I do see a t-score of negative 2.54 or 47. I see a p-value of 0.013, which is telling me that at the 5% level, yes, there is a significant difference between the time to travel for men and women. It's not a monstrous difference, but it looks like about on average, about 5-minute difference from our sample, 4 to 5 minutes. And that is considered significant based on this data set. Now, the thing that we've discussed so far is how do we then come back up here and fit a linear model to predict this. So let's kind of inject these indicator variables. I'll call this commute, we'll call it commute. And I'm going to fit a linear model, and I'm going to predict the time based on the sex for the data. It's actually the same exact arguments that we would put in to our standard t-test function. So I'll run that and I'll get a linear model. I'll look at the summary of that linear model, commute. And what do we find? Well, the first thing I want to show you is we have an equation. Our equation says that the time for the commute is equal to 26.8 plus 4.5 times, says sex m. So what did it do? R actually made the indicator variable for us. Now, what did it choose to put in the model? It chose to put male in the model. Why? I guess it leaves out the first alphabetically, so it left out F for the first alphabetically. And it keeps male, so what does that mean? Well, the 26.8 and the 4.5. Well, if you actually look back up at the t-test, and we'll go and raise this, make it so we can see everything. We notice the 26.805, that was actually the mean of the females. Which should make sense because if we have a female, the sex variable would be 0. So we would end up with 26.8. Now, where's the 4.5? What does that mean? Well, that's the indicator, the coefficient of the indicator variable for male. What that means is that compared to the baseline, compared to the reference group, which was female, males take 4.5 minutes longer. They are higher by 4.5 minutes. And if you check that, you would notice that 26.8 plus 4.5 is going to give you my 31.3. More importantly, I can look over here at the p-value, and you look at this and say, well, it's pretty close. I mean, they're almost the same. They're not quite the same, but they're really close. You wonder, well, why? I thought this was doing the same thing as the t-test. Well, if you recall in the video, and I believe that I might have misspoken or had a mistake on the slide, just a small one, is that if I run a t-test, there was the option to have equal variance. And I know I'm typing this down here. I'll copy it up top so you'll have it. If you type in it's either equal.var or var.equal. That's what I think I had wrong. Not var.equal. Let's see, what are the options if I hit tab? Oh, it doesn't even tell me. Let's try equal.var and see what happens. Equal.var equals true, saying that I want to assume that the variance of men and women are equal. It's a slightly more powerful test. It ran, and it didn't seem like that was the right argument. So let's try that one more time with var.equal this time. var.equal. var.equal, that's what it is. So again, ignore this equal.var, var.equal. So I'm saying I want equal variances. And if you look at the p-value here, you get a p-value of 0.0142. And if you look up at the indicator variable, it's 0.0142. The linear model with a single binary indicator variable is exactly the same as the t-test. If the slope is significantly different from 0, the difference between male and females, then we would say there's a significant difference. I just wanted you to make sure that you've seen that. I will copy this correct version and put it up in my file here so you can see that. So no matter which way we do it, we do get the same answer. Yes, with equal variance, it matches perfectly. Without the equal variance, it's very close, the var.equal, but we get most of the way there. So let's take one more look at a secondary data set. The data set I want to look at here is also in the Lock 5 data called Employee ACS. It's from a survey of different employees. I might have actually typed that in wrong, so let's actually Lock 5 data. And let's see what options there are here. I know there's some kind of an employee, might be employees. Employed ACS. I apologize for that, man. I've been a little off my game today. So I have head of the employed. I don't need the Lock 5 data anymore. Employed ACS. You see some information. We have the sex. That's already an indicator, literally an indicator variable for us. Age, whether they're married. Income, hours of work per week, what race they are they a citizen, health insurance, what language do they speak. Now, I really should find some more information here because sex is somewhat ambiguous. Does 0 stand for male or female? I don't know. I really would have to look at the help file, see if it gives me, and it does tell me. If you look at the help, that's what I would recommend doing. You see it says here 0 is female, 1 is male. 0 is not married, 1 is married. And if you look at race, we have multiple options. We have Asian, black, white, or other. So what I'm going to do is I'm just going to fit a model. I'm just going to try to pick some model that includes this factor variable. Race is a factor variable in this case. So let's go ahead and fit this model to predict income. So I'll say income model is going to be a linear model predicting income based on, let's predict it on the hours you work per week. So obviously your income should be higher with more hours worked per week, but not necessarily. The race, and I'll go and include sex as well. Now the reason I'm including all of those things is I want to look at, there are basically 3 different types of data in there. We have hours per week, which is numeric. We have race, which is a factor variable with 4 different groups. And we have sex, which is a binary indicator variable. So I'll run that, and then we'll look at the summary, and we'll try to figure out what it means. So when we look at this summary, we see a few things. We see the hours per week. We can see that hours per week is very, very significant in this case. Very significant, which obviously should make sense. It's saying for every hour per week extra you work, it's about $1,400, $1,470, $1,460. And then we see the sex. Well, we do see a slightly significant effect that the males are making more than the females, significantly more. It looks big because it says they're making $10,000 more per year. That seems like a ton of money, but it's saying it's borderline significant because there's so much variability in male and female salaries inside the males and inside the females group. Now here are the different races. You see black, white, and other. But we don't see Asian. Why not? Asian was determined to be the baseline. Again, why was that chosen to be the baseline? Simply, it was the first alphabetically. So what this is saying, that salaries, if I look at this, I can find out which, I should be able to look at just the coefficients and determine which race is making the most money on average in my sample. And I hope, take a minute to think about it. And when you come back, I think you'll agree that the white population is making the most money in this group. We see that's the largest coefficient. Now I want you to think really hard. Which group is making the second highest amount of money on average in my sample? This one's a little trickier. And the answer is it's the Asian group. And that one is a little tricky there, but you think, well, let's think. white is above the baseline, black and other are below the baseline, but the baseline would then have to be the second in order. Notice that the other group is way below the Asian group. Now, if you look at that, you can also look and say, well, these p-values, none of them really seem significant. So you can say, well, we can get up in arms about that the white race is making more money here, but really, that's just, I made a big point of saying, in our sample. In our sample, the white workers are making more money on average. But that's not, they're not making as much money on average that would necessitate me deciding, yes, there is a systematic problem here. It's just that by random chance, it appears that white race in this group had the most money. Now, if you want to really test, remember we talked about the F test. Can we test, is there a significant effect of race? I can type in ANOVA, income model, to look at the ANOVA table. And if you look here, you see hours per week, still very, very, very significant. Incredibly significant, no issues there. Sex, still borderline significant. Surprise. But then what about race? Well, notice here there's this little column that says degree of freedom. Degree of freedom means how many parameters did it cost me? Well, hours per week cost me 1 slope. Sex cost me 1 indicator variable. But race cost me 3. The question is it worth it? Do I get enough explanatory power out of those 3 predictors to say that race was a significant effect? And if you look at the p-value, you see no. There was no significant difference between the races. Yes, we did see that the white race had a higher and the other race was much lower, but it's saying based on all of the random variability, this could have just happened by chance. I see no significant effect. I would recommend you to take some time with these models on your own. Try to predict a few things. In fact, let me go ahead and do one quick prediction here. I'm just going to make one up. So I'll predict, let's make a data frame first. So my new data, I'm going to call a data frame, data.frame, in which the hours per week, we'll say it's a 40-hour per week person. They are, we'll say black, and we'll say it's female. So sex equals 0. So make my new data frame, and I will predict based on my income model. And I don't know when this, the data set, does it say when it was collected? It doesn't have a year on here that I can see. So yeah, so I don't know what year this is from. But if I was predicting based simply on my hours worked, my gender, and my race, so I have a black woman working 40 hours a week. I can also do a prediction interval if I like. So interval equals prediction. When I run that, I see that I'm predicting, so this must have been a while ago, I would assume, that the fit, I'm predicting that black female that works 40 hours a week will make about $36,000 on average. Now, the lower bound for my prediction interval is negative. It's basically saying, boy, it could really be anything. The upper bound is about $132,000 per year. So based on this year, there's my prediction is $36,000, but I do have a range, a plus or minus type range. I hope this gave you an idea of how to deal with indicator variables, and you should notice that it's very simple. I mean, you just go right into it just as is. You plug them in as a factor. I should make one more note, and I will. I know this video is getting a little long, but it's important to do this. I'm going to make a linear model for the MT cars data set. And I'm going to do it, I'm not going to store it in MT cars, so MT model. And I'm going to try to predict miles per gallon like I always do from the weight and the cylinders. And I'm just going to do it just like this. You can say, well, cylinders, there's 4-cylinder cars and 6-cylinder cars and 8. And I'm going to assume for now that those are the only choices. 4, 6, and 8-cylinder cars. That's it. So when I run this, and I look at the summary of the model, MT model, I'm going to see that it's giving me 1 parameter for weight and 1 for cylinder. Now that's a little bit misleading because what's happening is it's saying, oh, if you add 1 cylinder to a car, I'm expecting negative, a drop in miles per gallon of 1.5 miles per gallon. So, well, how can I restrict it to say I didn't really mean for it to be 4, 5, 6, 7, 8, 9. I just wanted 4, 6, and 8. That was it. Well, what I can do to account for that, let's come up here into our model again. I'm going to fit the same model, but what I'm going to tell, the way I'm going to tell R that this should actually be categorical is I'm going to coerce cylinder to a factor. And when I do that, it's basically saying, hey, by the way, R, there's only 3 choices here. Treat them as categories. Even though you see numbers, don't treat them as numbers, treat them as categories. And when I come down and look at my summary, now I see something a little different. I see the weight term, and actually the weight term is really similar. It's not the same, but it's very similar. But look at the cylinders now. I have 6 and 8. That means my baseline was 4. It says 6-cylinder cars have about 4 miles per gallon less than 4-cylinder, and 8-cylinder cars have about 6 miles per gallon less than 4-cylinder cars. This is important because the way it was written before, it says cylinder negative 1.5. So when you go from 4 to 6, it should drop 3 miles per gallon, 2 times 1.5. When you go from 6 to 8, it should drop another 3. But according to this, it's saying, well, it's not quite that simple. There's actually a bigger drop-off from 4 to 6-cylinder cars than there is from 6 to 8. So the reason I wanted to show you that is make sure that we're clear when we have a factor, or we have a variable that should be factors, it should be categories, but numbers are in there, you got to be explicit to the computer. Otherwise, the computer just assumes, hey, you said you had numbers? I'm going to treat them as numbers. So hopefully this gave you a good idea. Look through these data sets, make sure you get an idea of what's going on, and we'll move on to interactions next.